loading functions that are linked to your unit load cases in your FEA model. And the True QSC tool then becomes a very nice and easy to use post-processing tool to look at your very complex loading that you're going to get on your parts. And the third tool from Wolfstar Technologies is True LDE. And True LDE stands for Linear Dynamic Events. And its sole purpose in life is to be efficient, to be an efficient post-processor for Abacus linear dynamic solutions. So it's got a very narrow customer base, but it provides a very value-added service to those customers who are using Abacus linear dynamics, and we can make them understanding the results very, very efficient. And from the very beginning of our company, we've had a very strong relationship with FE-Safe. John Draper from FE-Safe, when he saw TrueLoad and what it could do, he wanted to form an alliance with us right away, because we make using fatigue-based tools very efficient and effective, because we're giving you the proper loads to do your fatigue analysis on. So if you have FE-Safe, all the products from Wolfstar Technologies output files that make using FE-Safe very easy and very effective. However, you don't need to have FE-Safe to use our tools, but if you have FE-Safe, we give you tools that make using FE-Safe much more efficient. Okay, so we'll get right into it now. TrueLoad. So the whole motivation for TrueLoad was quite simply, what's the load? So if you're developing a product like this motorcycle here, and if you're the design engineer or the analyst, how can you do your work if you don't understand the loading coming from a very complex events like this? So these events, it's impossible to measure the loads, it's impossible to calculate the loads, but yet as an designer, as an analyst, you're responsible for the durability of these parts. So how can you do it if you don't understand it? And so what TrueLoad recognizes is that the individual components on this motorcycle are basically responding linearly. So the swing arm, the crankcase, the frame, the handlebars, the gas tank, the fender, these are all components that are basically responding linearly to very non-linear loads. So we take advantage of that by placing strain gauges strategically on those components and backcalculate the loads on them, so we can then do design and optimization. So this is the technology we bring. And like I said, this is a first to market solution. It's based on influence coefficients. Influence coefficients have been around for 40 or 50 years, and historically influence coefficients have been a very labor intensive, 100% experimentally derived approach, and prone to lots of error. And what we've done with TrueLoad is we've taken out all of that iteration process in hardware and automated it in the FEA environment and with programming. So we've been able to take these very strong technologies and bring them into an efficient workflow in the FEA modeling community. So our software is ideal for any of these types of products. So, you know, whether you're on-road, off-road, aerospace, oil and gas, it doesn't matter. If your parts are experiencing loading that you can't understand, we've got a solution for you that will help you understand those complex loads. We've got customers in just about all of these product segments, and we've got very, very good retention and response from our customers. So, you know, the overall workflow for product simulation, you know, we all kind of deal with the same thing, right? We get models from the CAD department, so they're using tools like PTC, CATIA, SolidWorks. You know, they're using commercial CAD tools. Then we bring them into the FEA environment, and we use tools like ANSYS, Nastran, Abacus, and then you know, we bring loading in that we typically have for heuristic loading, or maybe some loading rules that we use, but we apply those to FEA models. And then once we get those results, we might want to do fatigue, and then we'll need to make up events, and we'll have events that we might be making up to generate these fatigue profiles. And then once we've gone through that loop once, we can hook on optimization tools like Tosca and EyeSight and those types of things to automate that and optimize our structures. So this is a basic simulation workflow that most people are using these days. And when you look at this space, there are mature, well-defined tools in all of these spaces, except the most important part, the loading and the event definition. that you're left up on your own. And if you get the loading wrong and the events wrong, who knows what your results are going to be. So this is the most important part of the whole process, and there aren't tools there. And what we hope to show you is that TrueLoad can fill all those gaps in a very robust fashion. So if we kind of take a look at historical concerns with loading, you can develop FEA models really well these days. You got good geometry, you got great measures, you got great material models, you got great solvers. And then the second you go in to submit your load, your solve, you're guessing at the load cases often. So if you're guessing at the loads you're putting on the structure, well, you're basically guessing at the results. You might as well get the crayons out and color the part yourself. If you don't know the loads going in, your results are just kind of a garbage in, garbage out situation. And what people traditionally try to do is they'll go out and buy load transducers, and they'll install these load transducers in their structures and try to measure the loads. The load transducers can be expensive. They add mass. They change the load paths. You've got to change the structure. So you're measuring something, whether it's the right thing or not, you don't know. And then worse yet is that when you want to work with the analysis community to use those loads, well, the analysts are working on the as-designed part and not the as-tested part. So typically, the analysts will have to rework the FEA model to make it look like the tested part so they can use the loads you're giving them. So this just isn't an optimal situation. This is just what people have got to deal with traditional load measurement. Other approaches that you might try to use is use strain gauge placement. So you'll look at your FEA model, come up with a couple of locations to place strain gauges. You might talk to some colleagues, come up with some more. And then you go place those strain gauges on the structure, and you get these time histories of strain, and they're very complex. It's not intuitive to understand what's going on. And you look at the strain response on the real structure, and you look at the FEA model, and you just scratch your head, and you can't understand the correlation. And so typically what will happen is you'll pick out one or two gauges in high strain areas at one or two points in time. You'll work on load cases that come up with and try to come up with some loads that sort of kind of correlate at those one or two spots in time. And then the next time you get into hardware, the next time you go through your design iterations, you get to the field and you find you missed something. And this is just wasted time, wasted dollars. This is typical. I have done this many times in my past. I know you have. This is just what FEA modeling and loading is without a tool like TrueLoad. So what's wrong? Your company is investing in all the right stuff, right? You're investing in great FEA software, skilled analysts. You're doing the right stuff by testing. You're working with tools like FESafe. Your companies are making all the right investments, but they're not getting the answers they want. Well, the problem is you got too many variables to manage. The gauge locations, the load cases, the quantity of data. These time histories of testing that you'll get, it might be 500,000 data points in this time history of testing. And the problem is at every point in time, you've got a unique loading recipe for each point in time that you've collected data. And it's just impossible to do manually. So you're in the kind of this no-win situation, and you're just left spinning your wheels. So this is what we're all up against. Well, the solution here is TrueLoad. So TrueLoad in 3 words is basically in situ load measurement. So we're going to take your component and turn it into a load measuring device by strategically placing strain gauges on your part in response to unit load cases. And we're going to leverage the FEA model and the test data to work together, and we'll get you optimal strain gauge placement and strain correlated loading. And the tool works as a plugin for Abacus CAE, Altair, and Beta CAE, and we are in the process of developing a standalone version that will work independent of your pre- and post-processing environments. So this is what TrueLoad does, and this is what it can bring. So the workflow for TrueLoad starts off with an FEA model. So we start off with your normal FEA model. This is just a typical FEA model that you would have. But rather than coming in and putting in one complex load case with all these loads acting on it simultaneously, I'm going to ask you to decompose that into a series of unit load cases. So an X component of load, a Y component of load, a Z component of load, maybe a pressure load, maybe a thermal load, maybe an inertial load, whatever you think it is, that if you could mix these loads together, could you approximate the operating environment? So that's the thought process. This is you being an engineer looking at your part and saying, how does load come into my structure? You solve the FEA model with these unit loads, and then we go into the pretest software. And the pretest software will look at the strain response to all of these unit load cases, come up with optimal strain gauge placement. We've got tools to let you reposition and reorient the gauges. But at the end of the day, we're going to get strain gauge placement and a correlation matrix that we're going to extract from the FEA model that basically is the strain response to each of these unit load cases. And then once we've got that, then we go in and lay strain gauges on the physical parts in the field and measure the strain measurement in the operating environment. And then we take those strain measurements then and bring them into post-test. And we go, and post-test is going to take the measured strain from the field times the correlation matrix from pre-test, and we'll generate loading functions. And now that we've got the loading functions, loads are loads are loads, we can run them into the FEA model, we can change the FEA model, redesign, iterate all day long, and it'll work, because loads are loads are loads, it doesn't matter. Now you can do this all manually with using your traditional FEA tools, or what I highly recommend is use the True QSE tool, which basically manages all the unit load cases and all the loading functions automatically and allows you to do this work in a very efficient manner. But you could do it with manual methods, or you could use the True QSE approach. It doesn't matter, it's up to you. And then at any point in time, now that you've got loading functions, then you can go off and you can go to tools like FE-Safe to do FEA-based fatigue, because now that you've got strain correlated loading, now your fatigue analysis is actually going to mean something. So when we look at this flow chart here, basically the top 4 blocks are you turning your part into a load transducer with true load. And the bottom flow chart are you doing design and optimization. Now that you understand your loading, you can go through and iterate and optimize your part now that you've got the loads that mean something. Okay. So I've got this player piano analogy as another way to understand this. So this is going to try to exercise the other side of your brain. So what I'm going to try to do here is show you. I'm sorry, 1 minute, please. I'm getting it. I think there's something kind of coming up here. I just want to look at something. All right, I'm sorry. So the player piano analogy. So if you were to design a player piano, we would first look at a piano and press each key on the keyboard one by one. And as we press the keys, we'd listen to the sound it makes, and we'd make a mapping between a key press and a sound. And what a normal person would call a note, I'm going to call a musical degree of freedom, and we're going to build up a matrix of these musical degrees of freedom. And then we listen to an analog concert, and we record this sound pressure wave from the concert, and then we go home at night then, and then we're going to decompose these sound pressure waves down to each of the individual musical degrees of freedom, or what a normal person would call transcribing it into sheet music. So then once we've got the sheet music, then we can make a player piano roll to reproduce the music. So true load works the same way. So with true load, we're going to take our component part, and we're going to put unit load cases on our part. Those unit load cases then are going to then create strain fields on the part. And now that we've got strain fields on the part, the pretest software is going to look at those strain fields and try to place strain gauges to uniquely identify each strain field. And then we place the strain gauges on physical parts, collect the strain data from the part, and then we take those strain measurements and we bring them into post-test, and we're going to take the strain measurements times the correlation matrix to generate the loads, and then we get these time histories of loads. These time history of loads are basically how much each one of these unit load cases participate in the full field response. So essentially, we can then take that and play back the time history of loads to reproduce the stress and strain events on the entire part. So those of you who are familiar with the concept of modal response analysis and modal decomposition, this has got a direct parallel to that approach. It's not the same mathematics, but it's a parallel set of mathematics as modal decomposition on a structure. Okay. All right, and so this is all based on linear systems and loads. So linear systems are where the loads are proportional to displacements, the displacements are proportional to strains, and the strains are proportional to loads. So this is a linear system. Now, I understand everything in life is nonlinear, okay? But we are going to turn our part into a load transducer. So we're going to stay in nominal strain areas on the part, and we're going to stay away from high strain gradients. We're going to stay away from where we've got welds. We're going to stay away from bolted joints. We're going to stay away from contact locations. We're just going to be out in nice nominal areas of the part because we're turning the part into a load transducer. Now, the loading can be as nonlinear as anything. Loading can be sinusoidal loading, it could be ramp loading, it could be impact loading. That doesn't matter. I just need the strain response to be linear. So I can take this diagram and turn it into a couple of equations. So the right-hand side, well, that's F equals Kx. That's Hooke's law. So if your structure obeys Hooke's law, then the corollary, which is the left-hand side of this triangle, which is strain times the correlation matrix equal to load, has got to apply. So this is what we're using for true load, and we're going to calculate forces as being strains from test times a correlation matrix from FEA. So this is what true load's doing. In the beginning, I mentioned that this is based on the science of influence coefficients. This is the governing equation of that. So we're going to take a look at that equation a little bit further. So here we got the strain matrix times a correlation matrix is equal to load. So in this example, I've got 3 unit load cases, and I've got 4 uniaxial strain gauges laid out on my structure. So I've got the columns of my strain matrix are the uniaxial strain gauges that we're going to lay on our structure. So I've got 4 uniaxial strain gauges for 3 unit load cases. This is my basic equation, and we're not going to get into any more real matrix math here, but I just wanted to show you the inside of what that all looks like, okay? So I'm going to go through the workflow on true load one more time, this time with a little bit of graphics behind it. So this is a headlamp that I use for my training examples. It's kind of a motorcycle-based thing because of my motorcycle-based background. So the analyst, when he looks at this part, he says, well, this part's basically experiencing base excitation. He says it's getting input excitation from the handlebars, from the front suspension, from the frame, from the engine. So he says that he can approximate what's happening on the structure as modeling as a base excitation. So what he's decided to do is restrain the bolt holes to ground and then put three acceleration fields on the structure. So 10 G's X, Y, and Z. These are his unit load cases on the structure. Solves it in FEA, and then he fires up pretest. And so pretest loaded up his 3 unit loads on the structure, and now he's got to select a subset of the model as candidate locations for placing strain gauges. So he goes in and selects these elements on the structure. Basically, he's going for the middle of the headlamp bucket and the middle of the legs. He's staying away from boundary conditions. He's staying away from where parts hook up to other parts. He's just out in the middle of the structure in these nice nominal locations. And then he goes in and tells true load he wants 6 strain gauges and asks true load to go find the gauges. True load draws up the gauges as little white lines showing the position and orientation of each gauge. He could reorient and remove them around, but if he's happy with them, he can say, I'm good. And then he places those strain gauges on the physical part and measures the strain data from the field. And now that he's got this measured strain data, the whole point then is to take the measured strain data and turn this into loading functions. And he's going to do that with post-test. And now in post-test, he's going to bring in the pretest file with a C matrix in it. He's going to bring in the strain data file from the field, and he's going to push this button to generate the loads. Now there's a lot of other things on this form where we can drop and map channels, we can plot data, we can prep things for FB safe, but really it's just bringing in the C matrix from pretest, bringing in the strain data from test, and pushing the button to generate the loads. It's about that simple. And then once you've got the loads, you can go off to FB safe to do fatigue analysis if you'd like. But what I highly recommend is you go into my QSE tool and this QSE file gets generated automatically, and it's got our 3 unit load cases and the 3 loading functions that were just generated all lined up. So then we can probe any node or element for any XY plots we want of any data component we want. We can generate operating deflection shapes, or we can go off to FE Safe and do fatigue analysis if you want. So this is a very nice interactive tool where we can go in and understand what's going on in our model from these loads. Now, the whole point is, once you've gone through this, we want to do redesign. So now we can go back to the original model, we can poke holes in it, we can thicken things up, we can change the structure however you'd like to do it. And now all we have to do is solve for the same 3 unit load cases that we started off with. And then we go back to our QSE file and we just point to the new set of FEA results here. And then we'll see the response based on these loading functions from these unit loads being combined by these loading functions here. So this is a very, very efficient way to analyze very complex time-varying loading on your structure. Okay, so we've got some customer examples here. This first one is a bulldozer, obviously. And this company, when I was talking to them about this, they had just launched this product, and they had a really hard time in development on this product. So the analysis guys couldn't correlate with the lab guys couldn't correlate with the field. Everybody thought the other guy didn't know how to do their job, and it was really a pretty bad situation. And so they said, here, Tim, you give it a try, okay? So we came in and we put XYZ unit loads on the front of the blade. There's a hydraulic cylinder here we had to actuate, and then on the back of the blade there was a mechanism. So we had 5 unit load cases. We laid 13 strain gauges on this thing. So we had strain gauges on the arms of the bulldozer and on the back of the blade. And then what you're seeing here is that the green curves are the measured strain that we from the field, and then we take those measured strains times a correlation matrix to get the loads, and the post-test software will take those loads now and go back in the FEA model and pull out simulated strains in blue. So what we've got is green is measured strain, blue are simulated strains simulated at the gauges, and they're seeing that we're getting very good correlation. So they were thrilled by this. They thought this was great. But they said what they were really concerned about were these forgings where they've got these welds and these stress risers, and they really want to understand what's going on there. So they laid additional gauges on here, like this gauge number 19, which is on by one of these forgings here on the structure. So we've got the gauge number 19 plotted up in green. And then we use the QSE tool to go probe the elements coming away from the weld and plotted those strains up in colors here. And you can see how well we got in correlation here between the measured strains and the simulated strains coming from QSE. So this is just a nice testament that says once you get the overall flexibility of the structure right, then these hot spot areas come along for the ride. And this is the type of things that you can do with true load. And this company could have never hoped to get anything near this good on their own. Okay, next example here is a crankshaft on a small engine. So this company was having problems with this crankshaft. It was failing on their dyno. So they were actually cracking the crankshaft end of the flywheel end of the crankshaft on the dynamometers, and they couldn't understand what was going on. So they worked on this problem for a couple of years, and then I came and talked to them, and they said, "Can you help me out?" And I didn't know much about engines, but we worked together, and working with the engineers, we came up with unit loads in the crank pins, so X and Y loads on the crank pin, and then they said that there's some modal content here. So we had a torsional mode and 2 bending modes of the flywheel on here. So we had five unit loads. We laid strain gauges on here, and what you're seeing on the top right are what I'm calling my bob and my wow plots. So best of the best, worst of the worst strain correlation. So green is measured, blue is simulated here, showing that we're line on line, like 0.01% error. And even my worst gauge, it might be 1% error. Okay, so this is the how well we get with strain correlation. When I reviewed the crank pin loads with the engineers, they thought the loads I was calculating was appropriate for the speeds the engine was running. So we had a sense check that we were calculating things right. We ran it all through FE Safe, and FE Safe identified this little area out here on the end of the crankshaft as being the area of maximum damage, which correlated exactly with where it was occurring on the real part. So really nice example of getting it right. Okay, I've got an airplane wing here. This is an example I worked up for a workshop I did at NIAR last year. So I didn't have an actual airplane wing, a wind tunnel, or the strain gauges. So what I did is I simulated that. I simulated a wind tunnel with a coupled structural CFD analysis here. So this is a highly nonlinear analysis, and I'm using this as my test article to see if I can reproduce the loading on this wing using true load. Okay. So so what we did is we went into the FEA model and basically placed the unit load cases of pressure loads on the wing. So we had 7 unit load cases on the top of the wing, 7 unit load cases on the bottom of the wing. True loads that place strain gauges at these locations here. The little green beam elements are showing the strain gauge locations. So these strain gauge locations are where true loads said place strain gauges on it. I went out and placed the strain gauges on the virtual CFD model, on the nonlinear model, and collected the strain off the nonlinear model. And then let's see how we did. So again, green is the measured strain, and then blue is the simulated strain once we back calculated the loads in the wing. And you can see that they're very, very close here. And we've got a cross plot here of measured strain versus simulated strain, and I've got nearly a perfect 45-degree line there. So that's a very, very nice correlation. And now that I've got those pressure loads, I can then go in and then calculate the operating deflection shape on the wing once I've got the loads measured. So an interesting thing about this, the true load work on this wing probably took less than 20 minutes. The CFD nonlinear analysis on my computer took 2 days to solve. Okay, so I could have laid strain gauges on an actual wing in a wind tunnel and had your results within 20 minutes, or you could have done a CFD analysis and taken days and been not sure whether or not it's the right loads. So, okay. This is an example from another one of my customers, Aaron's. They make high-end riding lawnmowers, zero turning radius lawnmowers, and commercial grade lawnmowers. And in this project, they needed to redesign the engine deck because they needed to provide airflow to the engine in order to get enough airflow to the transmission to cool off the transmission. So this was a redesign. The engine deck was working fine. Their baseline was fine. They just needed to come up with a way to provide additional airflow. So we, working with the engineers, we agreed that this was a base excitation problem. And so what we did is we put a lump mass to represent the engine on this engine deck, and then we put a series of X, Y, and Z acceleration loads on this structure. So this is, we're choosing to model the excitation of this as X, Y, Z acceleration loads. And then true load comes in and says, place strain gauges at these eight locations here on the structure, and then we place the strain gauges on the physical part, and we've got that. So the measured strains are showing here in green, and the blue is showing the simulated strains, and they're line on line. You can see our cross plot is line on line. And so what was interesting about this project with the customer is they had used their traditional FEA techniques then to, before I got involved, they had used their traditional FEA methodologies to design their first iteration. And so this one with all the slots here was their first iteration of the engine deck redesign. And the day I was there talking to them about doing this project, this design broke on their shaker in 12 hours. Okay, their design goal was for it to go 10,000 hours, and it broke in 12 hours. And I said, perfect, give me that FEA model. And then we took the loads from the baseline that we've got here, and we took those same loads, ran it into their structure, and you can see that the stress and strain responses are a lot higher. And then working with the design engineer there, inside of a week, we went through 5 design iterations with giving them the airflow that they need and the durability they need for the structure. So I've got durability plots in the next page here. So here's the strain life curve for their material, and what they want is 10,000 cycles. So basically, we're going to look for things are yellow or green or blue on these plots. So you can see their baseline is fine. There's some red here just because of the RBE and the FEA model. And then here's their first version of their design that they did on their own. And FE Safe was saying that this thing should have broken 10 hours, and they actually broke in 12. And so and it broke right through these two little ribs here, the exact location where FE Safe says it should have gone. And then here's our design iteration. So the first design was 2 sets of sheet metal riveted together. The manufacturing guys hated that, and then working back and forth, we came up with working with thicknesses of materials and weld patterns to come up with a final design that gave them what they wanted. And so we got the airflow they needed, and we actually got better durability than what they started out with. So this is what you can do if you understand your loads. You can get the design work done and get it done right the first time. So talking with them, this is how they estimate the things went. Okay, if they would have done it traditionally without true load, we would have gone through those 5 iterations. Each iteration would have taken 6 weeks. It would have cost $30,000 per iteration. So we'd have $150,000 in 30 weeks of time. And basically, engineering would have looked dumb the whole time, and we've just been guessing at each iteration. And with true load, basically, we've got basically 8 days of our time involved. And if you amortize the cost of true load on the project, you got $656 worth of software plus strain gauges, and we get it right the first time. We get high confidence, and engineering ends up looking like a hero. So this is really important. Engineering often gets saddled with some pretty hard projects, and it's nice to have a tool where you can come out looking good. All right, down to the oil and gas pieces. Okay, so I've got a blowout preventer and a flange, and we've got about 5-10 minutes here. So I'm going to try to get through this as quickly as possible here. So, Barack and the guys at Vias had given me this blowout protector and wanted to do a true load application with it. So working with them, we came up with these 2-unit load cases. So we have a compression load case and an internal pressure load case. So these were our load cases we put on the structure. And then we come into the true load software then, bring in that those FEA model results. And the first thing we need to do is we need to select our candidate elements for strain gauge placement. So I picked this face. And then we loaded in the unit loads from the FEA model. And then we just told true load that we wanted 4 strain gauges and for it to plot them up and show us. And I did a little bit of tweaking, a little bit of repositioning. I basically make sure the strain gauges were either parallel or horizontal, just to make them nice to lay. So basically we did a little bit of reorienting, and then when we're all done, we've got strain gauges that are laid out nicely on the structure. We've got an excellent condition number. So condition number is a mathematical thing for true load that we like to take a look at. And then what I did to test out the application a little bit more is I made up a simulated event. So basically I took that compression load and that pressure load and basically ran it through a sine sweep with some random noise on it, and ran that through and used that then, and we generated simulated strains on these gauges. So now these are perfect strains on these strain gauges. And to make the problem a little bit harder, I took these simulated strains and added 5% random noise on it. So now we've got basically something that might look like real test data with noise on the data. Okay. And then we ran that through a true load post test. And so here we've got the green. The green is the measured data from strain, and then we ran that through the equation. So strain times correlation matrix equals loads. So here's our 2 sets of loads that we calculated on the structure. We took those loads then, and they automatically generated the simulated strain, which is shown in blue here, and we get the cross plot, which is automatically generated, showing that we're getting really great strain correlation here. And then we take these loads then, and we can reproduce the operating deflection shape on the structure. Okay? So this is a very nice, simple way to understand everything going on in your structure with true load. Okay? And we're going to do the same treatment. And then just to go back and take a look at the loads we calculated with true load versus the original loads that we started off with on the structure. And you can see that the compression force load, we had a little bit more noise in it, a little bit more uncertainty, but it still followed the right trends there. And then the internal pressure load, was following much more closely. So showing that the pressure loads, the compression force was a little bit more sensitive to strain variation than the internal pressure. But nonetheless, these are still, I think, excellent correlations to the loading that was applied versus what we back calculated. Okay, same exercise now on the flange. I'm going to do the exact same thing. So now on this flange, we decided that there were 3 unit load cases. So we had a blind load, we had a moment, and we had a working internal pressure. So we had these 3 unit loads. We bring that all into the true load pretest environment. So we set candidate gauge locations, candidate elements. We bring in the unit loads from the FEA model. We tell true load we want 6 strain gauges and to go plot them up. And then we did a little bit of tweaking and repositioning, but not much. Okay. And then again, we've got this very, very nice condition number, good gauge placement, and then same exercise now. I basically took those 3 unit load cases and ran them through varying different time variations with randomness put on those time variations, and generate the perfect strain signals are our 6 strain gauges. And now we've got these 6 strains, added 5% random noise to make it a little bit more fair. And then this is the results. So green is the measured strain. These are the loads calculated by true load. Those loads go back in to generate the simulated strains. And we take a look at the cross plot. We've got nearly perfect correlation and an operating deflection shape. So a very, very nice set of loading. And now, if we go back and take a look at the load verification of looking at the original input loads versus the calculated loads from true load, showing that we're doing an excellent job in recovering the loads on this flange. All right, so this comes to the end of the presentation. Hopefully you've learned here that with true load, we'll give you optimal strain gauge placements. We're basically turning your part into a load transducer, and you're going to have high confidence in the loads that you measure off your structure. And then once you've got those loads, you can bring those loads into FEA, do redesign and analysis. You can bring them into doing fatigue analysis. And the most important thing that you're going to get out of this is that now that you understand the loads, you're going to make the right design decisions in FEA. So you're not going to have to go through the hardware iterations so many times. You're going to make the right decisions the first time because now you've got the proper loading on the structure. This is hugely important. It's going to save you so much time. And we didn't have time today to get into some very nice important features. The sliding load capability and the hybrid load capability that we've got in true load. I could spend another hour presentation on that alone. So maybe we could do a follow-up on that on another one of these webinars, but we've got some excellent tools here, and I thank you for your time. And I think we are coming, last slide here, just to show you the development. So we launched our Abacus version in 2011, the HyperWorks version in 2014. We just released the Beta CAE version in January of 2016, and I'm developing the standalone CE-tron version, which will be hopefully out in August this year. So we've got a really nice set of platforms we're supporting, and we should be able to work with any of your models, no matter what platform you're running on. Okay, thank you. So Renan, I'm not sure if there's any Q&A out there, but let's if there's anything that we need.